Hi, I'm Vienna, and today I'll be talking about soft processors, more specifically how they are implemented in field-programmable gate arrays. Soft processors control IP blocks that are accessed by the processor as peripheral devices or by using custom instructions. The flexibility of a soft processor is a huge advantage over hard processors because of the ability to be customized for a specific application easily. The soft processors are less likely to become obsolete because of the flexibility of their applications. The space constraints for a soft processor are nothing compared to a hard processor because the soft processor is able to implement all of the custom logic in the software. The cost of soft processors are generally less than that of hard processors because the hard processor logic needs to be physically built, whereas the soft processor's logic does not. Now I will discuss the applications of soft processors. In the communication field, Broadcom has used a 10-silica Extensa processor in their BCM 1500 project. The goal was to design reconfigurable communication components for broadband communication and voice, video, and data networking. There are 5 processors used in the Callisto architecture. This system is used for echolocation, data modem signal processing and delay equalization, and protocols for packet telephony applications. In the advertising field, the Advanced Electronic Designs Incorporated has built an LED sign for advertisement of JP Morgan Chase in Times Square in New York City. Using Xilinx components, the board is 130 feet in length and 26 feet high. The resolution is 2 million pixels, which is the highest resolution for a sign in the world. The board uses Xilinx Vertex 2 and Spartan 3 field-programmable gate arrays with over 1,000 pictoblaze processors. They use these processors for control functions and testing and debugging purposes. The processors make the debugging process easier, making the changes to the control functions also easier to implement because it can be changed in the program's code as opposed to physically. For security and authentication, the University of California in LA are using the Leon 2 soft processor for their ThumbPod prototype. This prototype is an FPGA-based prototype using Leon 2 on a Xilinx Vertex 2 field-programmable gate array. This prototype also has 2 coprocessors. The main core processor runs the embedded Java kilobyte virtual machine to help with the software development. The purpose of this prototype is to capture a fingerprint, extract the features, compare to a known template, and return with a matching score from 0 to 100. The current processor cores on the market include Microblaze. Microblaze is made by Xilinx. It has 32-bit reduced instruction set computer, 3-stage pipeline with variable length instruction latencies that range from 1 to 3 cycles. The Microblaze uses the Xilinx Platform Studio, which allows you to create a Microblaze-based system configuring the cores from the provided libraries. This soft processor is constructed around the Harvard memory architecture. It has 2 local memory buses that are used to connect the instruction and data memories. There is an on-chip peripheral bus to alleviate the system's performance bottlenecks. This is also designed to support the low performance and speed peripherals such as UART, GPIO, USB, and others. The Neos 2, made by Altera, has a load-store-reduced instruction set computer architecture. Many of the architectural parameters can be customized at design time. The Neos 2 has 16 or 32 bits of width in the data path. The register file sizes, which the cache size and custom instructions of performing the user-defined operation in the speeding up customized hardware is included. The NEOS 2 integrated development environment is what is used to allow building, running, and debugging software to work on the several platforms. The system on a programmable chip builder is used for the rapid creation and easy evaluation of the embedded systems. This diminishes the time used to set up the system on a programmable chip, so designs can be constructed faster. The Micro32 soft processor is made by Lattice. It has the softcore reduced instruction set computer processor that is easily added to an FPGA. This soft processor is completely customizable by the programmer, unlike other soft processors that only allow certain predefined architectures to be used. This uses less than 2,000 lookup tables, which makes embedded systems with this chip very inexpensive. There are 32 general-purpose registers, 32 external interrupts, and dual wishbone memory interfaces. This softcore can run at over 100 MHz on low-cost 90-nanometer ECP2 FPGAs. The SPRI system is the soft processor rapid exploration environment, and it functions to create custom soft processor designs. The figure shown to the right is a visual of the overview of the SPRI system. The SPRI system generates the synthesizable RTL, which allows the RTL description on benchmark applications to ensure the correctness of the processor and measure the number of cycles needed to execute the individual applications. The RTL is processed by CAD tools with abilities to accurately measure the area, clock frequency, and power. The performance and power of a soft processor greatly depends on the sustainability of the targeted application. The factors that describe the suitability of the sustainability of the targeted application are the type and sizes of the memory and peripheral buses, the size and model of address space, the type of controllers used like DMA and interrupt structures, the hardware accelerator capabilities for coprocessor functionality, and register file and execution units used. The design and development of soft processors comes from two factors: the cycle efficiency and the software interaction with the FPGA design and development tools. The cycle efficiency can be broken into many different factors: the ease and use of the feature sets, the design tools flow, the development environment tool maturity, the compatibility of the major software releases, the availability of training, and the quality of the tool tutorials, and finally the debug and verification capabilities. The tool suites within a program will include software and FPGA design development tools all in one. The interaction between the two, the co-design or platform development tool, need to be efficient. This interaction is responsible for the parameterization of the softcore and peripherals, implementation of the processor buses, memory maps, interrupt structures, and required processor peripherals. This also includes the compilation, linking, debugging, and downloading to the target processor. The debug capabilities are as listed: simulation, behavioral and timing analysis, embedded logic analyzers and embedded bus analyzers, software simulators, non-intrusive real-time software debuggers, trace capabilities, hardware/software logic analyzer triggers, board-level visual indicators, and standardized debug interface via the JTAG bus. Operating system layout. The operating system is included in most 32-bit processors to reduce the design time and provide an abstraction interface level to the software. The board support package that you can see under the Platform Development Tool block on the figure to the right can include the processor boot code and interrupt service routines for peripherals. Things to consider when choosing an operating system are API set, the level of IDE integration, tasking models, kernel robustness, preemption, resource allocation, protection schemes, and the operating system footprint. Most processors will have a pre-certified, pre-verified operating system to choose from. Embedded systems are systems of hardware and software working together to perform a specific function. The embedded system is normally composed of a microprocessor, onboard memory, output display, input device for the user to enter data, and the application software. Applications. Embedded systems can be used in automobiles, the medical field, industrial control systems, and entertainment electronics. Constraints. There are tight constraints on embedded systems for area usage, size, power consumption, and performance. Co-design methods. The hardware/software co-design is crucial to reducing the amount of time spent to develop and debug the system. Measuring soft processors. Area. The number of resources on the soft processor used are counted and equated into logic elements, which are used to represent an even metric for the area efficiency of soft processors. Performance. The performance is measured in both wall-to-clock time and instruction throughput per second in millions of instructions per second. The wall clock time is found by multiplying the clock period with the number of cycles spent executing the benchmark. The instructions throughput per second is found by dividing the total number of instructions by the wall clock time. Efficiency. The computing performance gained in instruction throughput per unit area in logic elements is measured in millions of instructions per second per logic element. This is a debatable metric to measure the area and speed of a soft processor simultaneously. Pipelining. A pipeline is the line of elements being processed one after another, each leading to the next element. The pipelines compared in these two figures are ranging from 2 to 7 stages, omitting the 6-stage pipeline. The area for each pipeline depth is shown in the top figure. As the depth line increases, so does the area. The performance of each pipeline depth in different benchmarks is shown in the lower figure. Integer functional units. The shift register is 1 clock cycle for every bit that is shifted. There are dedicated multipliers in architecture for functional units, and another option is to have dedicated multipliers for shared multiplier shifter units. Comparatively on size, the shared multiplier shifters are better. They can also match in performance with the others. Multiplier. The multiplier uses the dedicated multipliers from the FPGA architecture. The multipliers on the FPGA are area efficient, which makes the other options of lookup tables and flip-flops seem less efficient. The multiplication can be done quickly in the FPGAs. It only takes 1 or 2 cycles longer than an adder. Multithreading in a soft processor allows the area reduction in the system on a programmable chip implementations. This allows multiple programs to access the same IP without the need for the logic replication or the replication of full processors. There are 2 classes of multithreaded processors. The fine-grained multithreading only allows 1 thread to use instructions in a given clock cycle. The simultaneous multithreading allows multiple instructions from multiple threads to be issued between the same clock cycle. Thank you for a great semester. I hope you enjoyed my presentation.
Spooky, scary skeletons and shivers down your spine. Shrieking skulls will shock your soul, seal your doom tonight. Spooky, scary skeletons speak with such a screech.